Okay, the basic anatomy of a delta sigma converter, delta sigma A to D converter. It has basically two major blocks, the delta sigma modulator and the digital filter. They're typically higher poles. This is an example of a single pole digital filter. Beginning with the delta sigma modulator, it basically produces a count or a pulse, and the length of the low going of the pulse is determined by Vn. Vn goes through a voltage to current converter, and that current discharges this cap, which was previously charged by a set current source. And the output voltage of the cap feeds a comparator with a set hysteresis. And to refresh on hysteresis, basically the input goes in and reaches an upper threshold, and the output will go high. And then the threshold will switch to a lower one. So as the output goes low again, it'll reach a lower threshold and it'll go low. So basically it's charging and discharging within that upper and lower input thresholds. So what you get was the voltage here determines the length here, and the coming up count. So it clocks this, the output, and then it also clocks this counter, and it goes through the counter, takes a count, goes to a summer, and that is summed with the output that goes through an inverter with a added 1. I didn't show it here, but we're adding 1 for a 2's complement. So you're basically taking the count and you're minusing the output, subtracting the output, and multiply it times a constant, and then plus the previous output data or voltage or data, digital count at the, plus the previous digital count at the output. This might be made more familiar with a regular analog low-pass filter with RC. So VC equals Vn times 1 minus E times T, 1 minus E to the minus T over tau, and tau is basically R times C, the time constant. So if we set T for a first time constant, you'll basically get VC equals 0.63 times Vn. And then the remaining time, the second time constant, will be 0.63 times the difference between the previous V out times the current, the set Vn. So it does that continually up to the point where it pretty much approaches or gets to Vn. So that's where you can see the similarities of the digital filter. The pluses of a delta sigma A to D converter is that it reduces output quantization noise significantly. So and it does so by a factor. It's called the oversample rate, and basically it's the initial sample rate, which I call it clock 1, so F oscillator clock 1 divided by 2 Fn max, which is the eventual frequency you want to be able to sample and represent. So you pick a certain one. So 2 times that will meet the Nyquist, or almost pretty much meet the Nyquist criteria for 2 sample rates, and for a cycle. So you can pretty much, you're sampling out much slower than you are initially sampling, and there's some magic being done there. So with that oversample rate, which is the clock here divided by whatever 2 Fn you want, and it reduces the output power, noise power, significantly by that rate. So if you have a higher clock rate versus the output rate, then you can get pretty good reduction in noise power. Also, with this digital filter, you can determine what F cutoff you want. So in here you can inherently have T. And I don't know if I mentioned this. You were going through. I think I missed this part. So you go through the summer, subtract the output, and then you go through this divide by 1 over T, and that can basically be represented by multiply by T. So in essence, you have this formula which I mentioned earlier. So I don't know if I went through that part of it yet. So you can set that tau, and you can determine what cutoff frequency you want. It says 1 over 2 pi times RC, or 1 over 2 pi times tau, and tau determines how much you divided or multiplied the difference between the input and output digital setting or values. So the big pluses to that, I pretty much mentioned that. I think that's pretty much the gist of a delta sigma voltage, delta sigma A to D converter.